Hi, I'm Aries Itten, and this is our education tutorial, What is SAS Viya? Today I'll be discussing with you the SAS Viya architecture, and specifically how that relates to the way you access data and how data moves and is processed. I'm assuming that you have no prior knowledge of SAS Viya, and the objective is to give you a basis and starting point for going forward with some foundational understanding of SAS Viya. We'll start with the architecture. SAS Viya in a full deployment is a multi-machine distributed platform. Here's an example in the slide. Each box here is an individual computing unit, either a separate computer or a virtual machine in a cloud deployment. Each machine has its own disk storage, that is hard drive, its own memory, that is RAM, and a CPU or multiple CPUs for each of these machines. They're all going to be connected via some sort of network communication, probably Ethernet. Focusing first on the server controller and the server workers. These machines together provide a distributed multi-machine data processing environment, and we'll call this environment SAS Cloud Analytic Services. We'll often call it CAS for short. The CAS server would be all of these machines combined. Here we show 3 CAS server workers, but you can have as many as you need depending on the volume of data and the complexity of processing required. You can also scale up, so if you find that you don't have enough CAS workers for the processing that you need, you can always add more. In CAS, multiple tables can be loaded. These tables are retained in memory, not just available on disk on the hard drive. Each table is distributed in memory across all the workers and is processed in parallel with various CAS processing actions. In addition to the in-memory data, a permanent copy of the data can be stored on disk. CAS supports parallel loading from disk into memory and also parallel saving of the data from memory back to disk. The purpose of this multi-machine parallel processing is to allow you to process large volumes of data and perform very complex, resource-intense processing on big data quickly. The idea with in-memory data is that once the data is loaded from disk, it remains available in memory over time for repeated use by one user or by multiple users. This speeds things up because loading data into memory takes a long time relative to processing data once it's in memory. CAS is a shared server, so multiple users can actually use the same in-memory data for different processing tasks. SAS programmers using SAS Viya can interact with CAS or the CAS server from a SAS session separate from CAS called SPRE or SAS Programming Runtime Environment. Each user starts up a user session in SPRE. SPRE is where your SAS programs are initially submitted. You can use SAS Studio as the programming interface. Think of SPRE as where your good old SAS session is. You can execute the same type of SAS code in that SPRE session that you may have been doing for years. In fact, SAS 9.4 M5 or later or a newer version can also be used in place of SPRE. This allows you to integrate existing SAS 9 implementations with SAS Viya. Now, of course, if you don't have an existing SAS 9 implementation, the SPRE environment comes with Viya on its own. Users access a SPRE session, and the CAS session, in fact, from a browser on a remote client machine, generally using a SAS Studio interface. First, you start a SAS Studio session on the SPRE server machine. At this point, you can execute traditional SAS code, your good old data steps and SAS procedures, on your SPRE session without any use of CAS. But from the SAS Studio session, you can also start a CAS session on the CAS server. The CAS session is a multi-machine session. You'll have your own session controller, which is essentially similar to the CAS controller, and you'll also have session workers for performing parallel processing on distributed in-memory data. Depending on your administrator settings, you might have access to all of the workers connected to your CAS server, or you might only be given a subset of them to free up resources for everyone else. Each user gets their own SPRE session and their own CAS session. In this demonstration, we'll explore the SAS Studio environment, start a local SAS session on the SPRE machine, and then also start a CAS session on the SAS Viya server. We'll start by opening Google Chrome. And under SAS Viya bookmark bar, we'll navigate to SAS Studio. You can see it takes us to this address, server/SAS Studio. We'll sign in using our username, Lynn. And we don't want to treat Lynn as an administrator, so we'll click No to not sign in as an administrator. Once we've entered SAS Studio, we can see there's some options here on the left. We're looking at the Explorer tab. We might also want to look at the Libraries tab. This shows some of the SAS9 libraries loaded in. So it looks like we've already started our SAS session on the Spree machine. Under Explorer, we can see this is basically server files and folders on the operating system. So this object here, server, is in fact the SAS Viya server. It's server.demo.sas.com, but it has an alias here. And under server, we see we have this home folder, and this home folder points to Lynn's folder on the operating system of the SAS Viya server. So Lynn's account has some sort of access and has been given some folders, and here are the folders that Lynn has access to. So we're not going to see all of the root folders on the operating system, but just the folders that Lynn has access to here. Let's go ahead and look at these folders in a different interface just to verify that what we're talking about makes sense. I'll minimize SAS Studio in Google Chrome, and I'll open up WinSCP. I'll sign in as lyn.server.demo.sas.com. My password's already saved in WinSCP. WinSCP is a tool that allows me to copy files or folders from the local machine, the local client, to the backend server. Right now I'm getting this permission denied error just because it's pointing to a folder that Lynn doesn't have access to. I'll click OK. I'll just go back to home. And I'll actually just go back to the root directory here by clicking this slash. So here's the root directory we can see on the operating system. I'll make this full screen to see a little bit. Here's the client system here over our Windows computer here, and this is the Linux computer. To look at what we were seeing in SAS Studio, I'll go to Home, Lynn, and now we can see there's these 4 objects, sasuser.viya, demo1, demo2, and sales.csv. Just if I go back to SAS Studio real quick, we can see those are the 4 objects in Lynn's home folder. So since we've signed in as Lynn, we only have access to the files that Lynn would have access to on the operating system. But we could see that there are certainly more files on the operating system, other users, and then just the root directory. I'll close WinSCP. I'll terminate the session. Actually, I'll just minimize it. We'll leave the session open in case we want to come back to it. I'll open up mremote-ng, which is really an SSH tool to SSH over to the server. Once mremote-ng is open, I'll double-click Lynn to open up a connection to the SAS Viya server as the user Lynn. If I type in pwd, this will print my working directory. Here, I'll make this full screen a little bit. My working directory is /home/Lynn, so that's that same location that we were pointing to on the SAS Viya server. I could also just look at everything on the operating system, ls-l/, to look at the home directory on the operating system. So this is what we don't have access to in SAS Studio because they're not living in Lynn's home folder. But if we look ls-l/home/Lynn, we see the 4 folders in Lynn's folder. So we can see there's more folders that we don't have access to in the SAS Studio interface. We'll go back to SAS Studio. I'll open up this code demo1.sas. This has a bunch of content for the demo for the first section. We'll just execute the first few rows. The very first row's options and CAS session are just to terminate previously existing sessions and set some simple options. But the next code, we'll go ahead and run this code and look at it. We're assigning a live name to a local SAS in the local SAS environment. So this is part of our Spree session. This is our SAS session on the Spree machine. If we just look at the log real quick, I like to point out it gives me an error that says session my session not recognized. When I tried to end the CAS session, it tells me there's no CAS session open because you haven't started one. This was just in case we'd already run this code. When we assign the live name, we get live name MySAS was successfully assigned as follows. It's just a base SAS engine, base SAS library. So this is all part of our Spree session, and it lives here on the compute server. So this is all just part of our SAS session on the Spree machine. When I list all the libraries in the Spree session, before I do that, here it tells me a list of libraries in the Spree session. I won't look through all of these libraries, but if I click over here, libraries, it matches these SAS libraries. Maps GFK, maps, and now if I refresh this, we'll see that my SAS library that I just created gets added to this list. We look at some results. We also called this proc means on a local SAS table. So this is just all happening in the SAS session. So this is all in the Spree machine. We calculate all these means, all of these summary statistics, on a single machine, which is the Spree machine in the SAS Viya server. So this computation is not being distributed because we haven't made use of CAS yet at all. So far, we're just using the Spree environment. I'll go ahead and start a CAS session and list all of the CAS libraries available. So I'll run these lines of code. CAS my session. We have some session options, just the timeout options and the default CAS lib, which we'll talk about CAS lib shortly, as well as listing some information about different CAS libs. We'll start by just looking at the results. We can see the session my session successfully connected to Cloud Analytics Services. So this is the SAS Viya server. This is the CAS server controller, server.demo.sas.com. We see a CAS statement, and we see the session, my session, has been created. And we default to the CAS library, CAS user. When we listed all of these CAS libraries, this caslib underscore all underscore list, we see a bunch of CAS libraries. I'll just highlight a few. Here's the CAS user CAS library, so it's specific to the user Lynn. It points to this location on the operating system. I find this tends to be very useful if you want to put files in there on the operating system or pull files out of there on the operating system. It's nice to know where that path is located because it's sort of hidden a little bit in the operating system. We can also see, I'll scroll down, we'll look at the public CAS library. This is sort of a CAS lib that's shared between all users. We get this description accessible to all users, and we can see here's another location where the path is located. So if we wanted to move files to there, again, these are where these CAS libs are actually located on the backend server. So you can see even though we have access to this server folder, Lynn's home folder, by default, that's not where her CAS lib is. So we might want to put another personal library there if we were so interested. For now, we'll just be loading files into Lynn's CAS user CAS lib. And we'll talk about what those CAS libs are in the next section. In this next section, I'll explain CAS libs and how to use them. CAS libs represent a way to reference an in-memory space for loading and accessing one or more in-memory tables. Each CAS lib is also associated with a data source location on disk, where data can be permanently stored. So to repeat that again, each CAS lib are a way to identify a set of in-memory tables, and each CAS lib is also associated with a disk location for storing a copy of tables on disk. The disk data source can be in the form of SAS datasets, CSV files, Excel worksheets, database tables, SAS HStat files, and others. Sometimes these objects can even be images or audio data for doing deep learning. CAS libs also include authorization information, such as user IDs and permissions to control access to data and other resources. Just like traditional SAS libraries, multiple CAS libs can and typically are defined for each CAS session, each with unique data source information, but also specific authorizations for different users and groups. This is important because CAS is a shared server environment, so you need to be able to control who has access to various data sources and what type of permissions they have for that data. In the demo I just did, I started a SAS Studio session on Spree, and I started a CAS session on the CAS server. In the next demo, I'll show you how to access data stored on disk and move it into memory on the CAS server. And you need to be able to do that because you cannot use CAS data in a SAS procedure and do any processing until it's been loaded up into memory. Recall that in-memory tables are automatically distributed across all worker nodes. So how do we load tables into memory? One method is proc CAS util. With proc CAS util, one of your choices is to move data stored on the Spree machine into CAS. That is represented here as the folder icon with the little purple squares on the yellow Spree machine. So data is stored there in the Spree machine on disk, and that data is first moved from Spree to the CAS session controller machine. From there, the session controller distributes the data across all CAS workers in memory. To do this, you can either use a load data equals statement and name a SAS dataset from your SAS library in your Spree session, or you can use the load file equals statement and name a file from the Spree machine file system. These can be CSV files, a worksheet from an Excel workbook, and a few others. With the load data equals, you specify a SAS dataset in the form of saslibRef.datasetName. With the load file equals, you specify the file system file path and name. You can also load data from disk on the CAS session controller into the session workers. This data source is now represented in the diagram as the folder with the purple squares on the session controller machine. The CAS session controller process manages this operation. To do this, you'd use the load CAS data equals statement. On the load CAS data statement, you simply name the file and the CASLib that points to that file. You don't specify the file system when you name the file because the CASLib definition already defines that physical location. So you're loading data from the CASLib, which specifies a location on the server. In some cases, data can be loaded in parallel directly to each CAS worker. This can improve the performance of the load for large volumes of data. Keep in mind that no matter how we load data into in-memory CAS tables, whatever the origin of that data, it's all directed from the program code we submit from our SAS Studio session running on the SPRE machine. Here's an example of a valid load CAS data statement for parallel load to CAS workers. This requires the use of a file stored in SAS HDAT format, which is a SAS format designed specifically for parallel loads and saves. Think of it as a distributed form of a SAS dataset, distributed across these session workers, or the worker nodes in the CAS server. Once data is in memory, it becomes available for use in data steps or proc steps that are executed on the CAS server through a CAS session. PROC-MD summary is a CAS procedure. In your SAS Studio session, you submit PROC-MD summary and you name an in-memory CAS table as input. SPRE will know to send the request to run this proc to the session controller process, which will coordinate the execution of the proc in parallel in each of the worker nodes on the distributed in-memory data. Here, I've shown you how to name that in-memory table on the data equals option of the procedure. It is a two-part name in the form of caslib.tablename, just like you name your SAS datasets in SAS libraries with a two-part name. But in this case, CAS user is a Caslib rather than a SAS library. Non-CAS procedures and other processes that do not run in CAS can also use CAS in-memory tables as input. In such cases, the data is moved from CAS back to the SPRE machine for processing in the SPRE session. Proc print, for instance, is such a procedure that only executes in SPRE and not in CAS. This is not practical for large volumes of data, but is often used for subsets of data or summary results produced by CAS analytical procedures. In this demonstration, we'll look at some options for adding data to Caslibs and executing SAS procedures against data that's in memory in the CAS server. In the last demonstration, we ended by listing out some of the Caslibs that we had. We explored just a few. We looked at CAS user lin. We saw that it was a path Caslib, so it points to some location on the operating system. We also looked at the public Caslib and saw that it also was a path Caslib, so it points to some location on the operating system. Why don't we look at some of the files that are located in those Caslibs? So we'll submit this proc CAS util code, and we'll just list files in disk for CAS user, as well as tables in memory for CAS user, and of course the same for the public Caslib. So we're going to look at files living in the hard drive location, as well as tables in memory for both the CAS libraries. I'm going to change the option a little bit just so we can see the results a little bit more easily. Let's look at some of the results here. We see files on disk for the CAS user CAS library, and we see here's some information about the CAS user CAS library, all the information we saw in the log earlier. Here's all of the files in that location on the operating system. So we see we have sales.xlsx, which we saw in the folder a little bit earlier, but this is a different location. Some other tables, just to point out, there's some SAS HDAT files, a SAS 7 BDAT file, different kinds of data files. If we go down to tables in memory, we see that although it gives you information about the CAS user CAS library, it doesn't list any files in memory or any tables in memory below here. So if we go to the log, we can see this note here, and I'll just click the note up here, but we could scroll through the log to find it. No tables are available in Caslib CAS user lin of Cloud Analytics Services. So there aren't any tables in memory here yet. If we look down to the public CAS library, we get more information on the CAS library, as well as all of the files living in the operating system. Here's some different files. Some of these were created by other users. You could see group SAS. Oh, I guess owner CAS. So these were created by different users. And once again, there's no tables in memory. We go over to the log. No tables are available in Caslib public of Cloud Analytics Services. So far, we just saw some files living on the operating system, but no tables in memory yet in either of these CAS libraries. Let's load a table into memory. We'll run a CASUtil to load CAS data sales.xlsx. So this is a file that was already on the operating system in the CAS user folder on the operating system. So we're basically just loading that file from the operating system into memory. I'll just execute this real quick. And we see the results. Well, at the very end, we listed all of the tables in memory in the CAS user CAS library, and we see that the sales table is now loaded into memory in the CAS user CAS library. And we see that its source is sales.xlsx in the CAS user CAS library, which is where we loaded it from. If we went to the log, we could see how long that it took to load it, and we could see that it processed the request. I guess I was going to point out, here we go. Cloud Analytics Services made the file sales.xlsx available as table sales. So it's now loaded it up into memory for us. I'll go back to the code. So now that we have a table in memory, we feel like we should be able to execute a SAS procedure against this table. So let's run it, and we'll see that this doesn't quite work. And I'll explain when we look at the error why it doesn't quite work. So we call procmd summary, which we know is a CAS procedure, so it can execute on CAS data. And we use data casuser.sales. So let's run this. But we don't get any results. We get an error that says libref casuser is not assigned. So although we have a CAS library named casuser, and we know it exists on the CAS server, our local spree session right here doesn't know anything about that casuser CASLib. So if I click libraries here, we see all these SAS9 libraries. So we see all these libraries on the spree machine, but we don't see any libraries on the CAS server because we have to tell spree about these libraries before we can use them. So let's go back and do that and see if we can get this procmd summary code to run with no errors. So I'll go back to the code tab. I'll scroll down. Here's the lib name statement. I'm going to assign a local caslib to allow spree to access the data. I sort of think about this as telling spree that we have this caslib and we want to use it, and here's where it is. So we'll run this code, we'll run the lib name statement, and then we'll rerun the procmd summary code, and we'll see that this time we get the results that we want. So we see libref casuser was successfully assigned as follows, and just note that immediately it refreshes our libraries tab, and we see this casuser CAS library here. We also get the procmd summary that executes successfully, and it produces some output data. So we create this data table, salary summaries, that contains the summary information. And notice this data table is an output table that's actually been added to the casuser library. So if I open up the casuser library here on the left, I can see in addition to the sales table that I loaded into memory with the procCasUtil, here's the salary summaries table created by procmd summary. I'll go back to the code tab. So that's a good lesson that you just want to make sure you have access to your CAS library in the spree session before you execute SAS procedures or CAS-enabled procedures that call that CAS library. Now we'll go ahead and use a procedure that'll only run in spree. So it's this procprint procedure. Procprint isn't a CAS-enabled procedure, which means it won't run in the CAS environment. We still get results even though we call it, so just pointing back to the code because I didn't highlight this, we call this print procedure against a table living in the CAS user library. And we're getting some results here locally in the spree environment. But if we go to the log, we can see that nowhere does it talk about using cloud analytics services. So this procedure gets executed locally in spree, which means that basically this data gets brought locally to spree to be executed on this single machine environment. I'll go back to the code. We'll just look at a couple of different examples of ways to get access to tables in the CAS environment, essentially to get tables into the CAS server. We can load a table from a spree library into a CAS library so that it's then loaded into memory on the CAS server. So we'll use procCasUtil to do this using the load data statement. We can see that the data has been loaded. Here's now our tables in the casuser CAS library. And the table we just loaded was the employees table loaded into the casuser CAS library. But this time we loaded it into the casuser CAS library from the MySAS library. We had this employees table in the MySAS library living in the spree machine. If we go to the log, we can see that the table mysas.employees was added to the casuser library. I'll go back to the code. So although we could move tables from SPRE, essentially from the SPRE environment into the CAS environment using proc-cas-util, we could also do it using a couple of different procedures. We could use it as a table created using the data step. So in this data step code, we have a table. The set statement calls a table in the my.SAS library, but it outputs a CAS table, so it loads the data into memory. Or we could use a procedure like proc-SQL, whose output can be specified as a CAS library, as a table in a CAS library. So the create table statement, instead of specifying a SAS library, we can specify a CAS library, and this proc-SQL code will, just like this data step code, load our output data into CAS. So I'll run both these procedures. And we can see in the log, the dataset CAS users employees was loaded into memory, employees 2, as well as CAS users employees 3. So the data step code loaded CAS users.employees 2 into memory on the CAS server, and the SQL, this proc SQL code, loaded CAS users.employees 3, well, created it and loaded it into memory. So if we look back at the CAS user library, we now have employees 2 and employees 3 as in-memory data tables. We can look at the output data to see that these are the CAS tables that we've now loaded. CAS user, CAS user. Go back to the code. So a bunch of different ways to load data from basically from your SPRE environment up into CAS or from your CAS user library. So we've sort of looked at ways to either load data from your local SAS environment, your local SPRE environment up to the CAS server, or from living on the CAS server up into memory. What if we have a file on the SPRE machine, but it's not in any sort of SAS library or anything? So it's not in a local SPRE library like my SAS, it's just on the hard drive of the local SPRE machine. We can load those tables into the CAS server as well. So we'll use the load file option in proc-cas-util to load a couple of different files. In this case, these are actually from the server. So these are files on the Linux server, but they're not located in any CAS library. So we're loading them up into the CAS library from some location on the server. So this could be data on the server that we don't have a library pointing to. I'll go ahead and execute this code. So we can see the CAS-util procedure shows all the tables loaded, and we now see we have this my Orion and sail from at CSV. So if we go back to the log, sort of scroll up, we see load file orion.xlsx, and we output it as my Orion. So we have a table CASUser.myOrion that we created from this file on the operating system. And we also load this other file that's a CSV file, and we have to specify some import options for the CSV file, basically the CSV encoding, and the fact that we want to get the column names from the CSV file. And we output it in the CAS user library as sales from CSV. And we could go ahead and double click this. So I'll just double click one of these tables in the CAS user CAS library to look at the in-memory data. So now this essentially gives us a view of the in-memory data. And of course, it's not going to show us all the data, so it only specifies some of the rows. Well, I guess these are all the rows in the data, actually. But it allows us to only display a subset of the rows in case the data table is too big, so it doesn't try and bring all the data from the CAS server over into this graphical interface. But this allows us to explore our data. And we've seen in this demo a bunch of different ways to get access to our data in the CAS server. So we could load it from the SPRE machine up into memory using a SAS library. We could load it from the CAS machine up into memory using a CAS library, or we could load data from the operating system up into memory, skipping the libraries altogether. So a bunch of different options. The best way I sort of think about it is generally whenever I want to use a new option, I generally have my favorite way to load data, which often is putting it in the CAS library and then loading it into memory. And if I want to use any of the other methods, I might just look up a table in the documentation to list all the different ways that I can get data into CAS. And in fact, since I've taken this course, instead of using the documentation, I might just use the course notes. In this section, I'm going to talk more about Caslibs. There's more to the story on Caslibs. Additional Caslibs can be added during a session by the user. To do this, you do need to be a user who's authorized to do so. This is done with a Caslib statement. You choose a name for your Caslib, here it's my CAS, and then you specify the physical location for the disk copy of the CAS tables in the Caslib. Here we specify a file system location, /workshop/CASServLoc. This location, in this case, is a directory on the CAS server machine. When you define Caslibs during a session, they're typically defined only for the duration of that session. So you therefore need to redefine them in each session that you want to use them. In contrast, global Caslibs are predefined and are available every time you start up a session. So the Caslibs we saw earlier, including CasUser and the public Caslib, are predefined. Permissions are used to control who has access to each of these global Caslibs. In CAS, we also have two types of in-memory tables. Unpromoted tables, when loaded into memory, are only available in memory in the session of the user that loads them. When that session ends, the tables are dropped from memory. Promoted tables, when loaded into memory, remain in memory even after the session ends. That means that any user will have access to that in-memory table in subsequent sessions, assuming they have the proper permissions. You can only promote tables that are in global Caslibs, because of course if the session Caslibs exists and they have tables in them, those Caslibs will disappear when the session ends, and the promotion wouldn't mean anything. In this diagram, a SAS Studio session has already been started on Spree, and a CAS session has been started on the CAS server. A table has been loaded into memory, but the table is not promoted. So this table loaded into memory are these purple dots, and it's not been promoted. So it's depicted as being in the session only. Then the CAS session is ended with a CAS my session terminate statement. One way to do that is to submit the session statement. The session goes away, and the in-memory table is also removed from memory. So the data is essentially deleted unless it's been saved to the hard drive. The table could still be loaded again in another session if there's a stored disk copy to reload. And this would be that SAS HDAT file we saw earlier. But an in-memory table can also be promoted so that it's not eliminated when the session's eliminated. So if the in-memory table's in this global Caslib, we can promote it. Here the promoted table is depicted in memory on the worker nodes. It's not simply on the session nodes, but it's actually here on the worker nodes, indicating that although it's available to the session, it's promoted. So then when we cancel the session or close the session by using a terminate statement, the in-memory table exists on the worker nodes, not just in the session. So it persists in memory. This table is retained in memory even though the session's removed. Then, when a user starts a new CAS session, since the table's still in memory, they can still access this global table from a global Caslib. In fact, each session that starts will have access to this global table, assuming that the session owner, so whoever starts the session, has permission to look at this table. So global Caslibs are available across all the different sessions. However, only promoted tables remain in memory after the sessions are completed. Of course, you can't promote tables that aren't in global Caslibs. In this demonstration, we'll look at Caslibs, the difference between session scope and global scope Caslibs, as well as the difference between promoted and non-promoted tables in Caslibs. So first, we'll just create a new Caslib named myCas that points to this location, workshop/SAS CAS serve loc, and we'll list all Caslibs in the CAS session. So we see we just added the Caslib myCas, and it's now the active Caslib. And if we look at it, we see that it is a local Caslib, which means that it's session scope. So if we look at some of the other Caslibs like public, it's not a local Caslib, or even CasUser, which although it is a personal Caslib for our account Lynn, it's not a local Caslib, which means it's not session scope, so it'll persist beyond this session. Currently, the myCas Caslib would be removed if the session were to end. Let's go back to the code. Let's look at some files in our Caslib, files and tables. There are currently no in-memory tables, so we could go to the log and see. No tables available in Caslib myCas of Cloud Analytics Services. However, there are a few files in the operating system location. It looks like we have the products Excel file and the profit SAS dataset. So let's go ahead and load some of these into memory. So we'll run some code. We'll run some proc-cas-util code to load some data into memory. In this case, we'll load profit into memory in the myCas library, and we'll load products into memory in the myCAS library as well. However, we will promote the products file. So we'll see if that's a possibility here. Go ahead and run. Spoiler alert, it probably won't work because it's a session scope Caslib. So execute this. It tells me the error stopped, the action stopped due to errors. Error, you cannot promote an output table to a session local Caslib. So what's happened here is our Caslib myCAS is session scope, which means when we end our session, it gets removed. But we tried to promote a CAS library, an in-memory table in this library saying, when the session ends, please keep this table in memory. But the entire CAS library is going to be removed from memory, so we can't promote a table in this Caslib. We'll go back to the code and see ways that we can promote tables. So in this case, we'll load data from a SAS data set into our CAS user CAS library, and we will promote that data. We'll load a SAS data set from our public CAS library, which is already living in the CAS library folder. We'll load that one into memory, but we won't promote it. And we'll also load some data into the public library from a path. So we're loading data in 3 different ways. This is loading data from a SAS data set using the load data statement. This is loading data from a Caslib server location using the load CAS data statement. And the final one is just loading a file from the CAS server operating system using the load file statement. Incidentally, the final table we do want to promote, so we will see how that works. We'll run this code. We see that the SAS help table was successfully added to the CAS user CAS library. We see that the goalies dataset was added to the CAS library public. And we see that the table orgdim was added to the CAS library public as well. We'll have to explore to see the promoted tables. So let's display the tables in memory now that we've loaded some tables. First, we'll look in the public CAS library. We have 2 tables, goalies and orgdim. If we scroll over to the right, we don't even have to scroll that far, but we see that goalies is not a promoted table, but orgdim is a promoted table. And just looking back at the code real quick, here we loaded the goalies table into the public CAS library, and we chose not to include the promote statement. But here, the orgdim file, we did include this promote statement right here. So we're loading this data into memory and then promoting it so it persists outside of this session. Just looking back at the results, we also have the same results for the CAS user CAS library. It's got a little bit more data because we've been sort of consistently loading data into it. But we see none of the tables are promoted except for this one table, 1986 baseball data, the baseball table. So if I go back to the code, when we loaded the data into the CAS user CASLib from sashelp.baseball, we included the promote statement. Since CAS user CASLib and the public CASLib are both global CAS libraries, they're not session scope, they'll persist after our CAS session has ended, we are allowed to promote tables into them. So if we look here, we now have 2 tables that have been promoted. The baseball table in the CAS user CAS library and the orgdim table in the public CAS library. All of the other loads that we've done were not promoted, so they're only session scope, which means when we end our session, they'll disappear out of memory. We'll go ahead and experiment with this by ending our session, starting a new session, and then executing the list tables in the proc-cas-util list tables functionality to see which tables are still in memory. So I'll run this next fragment. We see that our session successfully terminated. I just look at the log. Deletion of the session was successful. If we look at the results in our public CAS library, the only table in memory is the orgdim table, the one that we promoted. If we scroll down to the CAS user CAS library, it's even more dramatic. All of our data tables except for the baseball table were removed from memory. Now, in theory, there could be a concern that these tables are deleted and lost, but of course, we loaded them from the hard drive anyways, so those tables are still present on the hard drive. They're just not available in memory for doing procedures and processing. We talked about loading tables into memory, but if you create tables in memory, How do you save them so you have a permanent disk copy? Saving data is important if you need it to be available over time. In-memory data will disappear if the server fails unexpectedly. You may not be able to hold all tables in memory at one time, or you may want to export the data to another application. One way is the saved statement in proc cas util. When saving to files on the CAS server, you can use cas data equals and name a file system file. This slide lists the file format supported for that: SAS 7 BDAT, CSV, Excel files, jump files, SPSS files. But keep in mind that you can also save to database tables. That's not covered here. This is an example of saving to an Excel workbook. This, like most formats, will be stored in the file system on the CAS server machine. For SAS HDAT files, you can save those to a shared network location accessible to each CAS worker. This save can be done in parallel from each CAS worker. So we see in this slide, the little in-memory data table living on the session workers gets pushed into a hard drive space associated with that session worker. Because it's in parallel, it can save faster and load up into memory faster. Here is an example of a valid save cas data equals for distributed SAS HDAT files. And we'll see some more examples of this in the following demonstration. In this demonstration, we'll create an in-memory table using a CAS-enabled procedure, and then we'll save that in-memory table on the hard drive of the CAS server. We'll start by just connecting to the CAS user Caslib, and then submit a procmd summary procedure to create an output CAS table, CASUser.stats by position, which is basically summaries of the CASUser.baseball table. After we do that, we'll use the proc cas util statement to save this CAS table, stats by position, in the Caslib CAS user, and we'll use the file type auto, which means we'll let it choose the best type to save the file. Since it is a distributed in-memory CAS table, the best file type when you use auto will be the SAS HDAT file type. And we'll replace it in case there's any files already on the operating system. We'll then list the files in the CAS user Caslib to see what sort of files we have. I like to point out here, we didn't specify that we want to save this stats by position in the CAS user Caslib, but since that's the Caslib where the in-memory table is living, that's where it defaults to saving. If we'd want it to save it on the hard drive in a position or in a location corresponding to a different CAS library, we could have specified that with the out Caslib statement. We'll go ahead and run this code. Here we see the CASUtil procedure. We asked for it to list files from the CASUtil procedure. And importantly, the one that we wanted to highlight was stats by position.sashdat. And we can see it was last modified, well, this is the day I'm recording it, but for me, this is the newest day. So it was last modified most recently. So this is the table that we just saved. And we chose no encryption method because we didn't specify anything. We can go to the log real quick just to see. We connect to the CAS library. And then we save this file. Cloud Analytics Services saved the file stats by position.sashdat in Caslib CAS user. And this would be a distributed file on the CAS server. So it'd be saved across the different worker nodes so that when we load, we can load in parallel. Finally, a few words about where SAS programs execute in SAS Viya. There are in fact two places where your SAS code now executes. Things either execute in the CAS session or they execute in the SPRE session, that is the SAS Programming Runtime Environment. This matters because it can affect performance. It can affect where data has to be moved in order to process, and only CAS processes execute in parallel in a multi-machine environment. Some general statements are the following. Data step code, proc-fed-SQL code, and some SAS Foundation procedures might be able to execute in CAS if CAS tables are used, but certain language elements, if used, result in downloading the CAS table to SPRE for processing. A simple example is if we use data step code with the lag function, which looks one row behind, that will guarantee that the table is moved to the SPRE environment, because that lag function doesn't really work in a distributed environment. Any procedures executing in SPRE using CAS tables as input can pass where clauses to CAS. So what that means is that the CAS environment does the where clause and subsets the data, and then brings some subset to SPRE for analysis. Finally, there are new SAS procedures that only execute in CAS. These are procedures essentially designed for CAS, for the CAS server. We'll start with the data step. One requirement for data step execution in CAS is that both the input dataset and the output dataset must be CAS in-memory tables. But certain data step language elements, if present in your code, will prevent the data step from executing in CAS. For example, that lag function I mentioned. The data step always executes in a single thread in SPRE. In CAS, the data step executes in threads in parallel across the CAS worker nodes. Certain data step language elements prevent CAS processing and cause the CAS table to be returned to the SPRE session for processing. Documentation for using data step in CAS is available in great detail. There's a whole section on data step programming for CAS. DS2 or data step 2 code can execute in CAS as long as you use the sesref equals or session reference equals option and name your CAS session, and you use CAS tables for both the input and the output. A DS2 data program only executes on a single worker node. However, DS2 threads will execute across the worker nodes. So, just like in base SAS, you need to execute DS2 threads in order to accomplish parallel processing. Essentially, you specify the distributed execution across different threads in your code. As far as executing SQL code in CAS, you need to use proc fed SQL. With the sesref equals option, and if you select from a CAS table, it will execute in CAS. Proc SQL on its own does not execute in CAS and will only execute in SPRE. Thus, if you want the distributed processing, you'll want to use the fed SQL procedure. When using a non-CAS enabled procedure, in other words, a procedure that only executes in the SPRE environment, if you use a CAS table as input and you use a where statement, the where subsetting will be executed in CAS and only the subset will be returned to SPRE for further processing. If you set the option message level equals I, you will see information in the log verifying this. In the documentation, you can see a list of base SAS procedures that are CAS enabled and will execute in CAS if you use a CAS table as input. I have listed them here and on the next slide. So we've got proc append, proc contents, proc copy, proc datasets, proc delete, proc ds2, proc fed SQL. It's a lot of data manipulation procedures. Proc format, proc means, proc report, proc summary, proc tabulate, and proc transpose. There's also a collection of CAS actions that we can execute using proc CAS, but that's not going to be the focus of this course. However, I like to mention that there are more options available in the CAS server using the CASL programming language. And we have another education tutorial by my coworker Aurora on that very subject. For SAS Viya, there are a very large number of procedures that are designed specifically to execute in CAS. Depending on the SAS products you license, you will be able to use these. And you can see them all fully documented in specific sections for each type of SAS license. Here I'm showing a list of these document sections, so there are many procedures under each of these categories. For example, under SAS Visual Data Mining and Machine Learning procedures, there's all kinds of predictive modeling procedures like decision trees, gradient boosting, and neural networks. There's even deep learning models. To finish, I'll just leave this recommendation slide up. There's just some basic considerations with respect to performance tips and considerations when developing code in the SAS Viya environment. We want to avoid processing large CAS tables in SPRE. When we have big distributed tables, we want to leave them on the CAS server so that we don't have to bring them across the network and so we can process them in parallel rather than on the single SPRE machine. In general, we want to use CAS to generate summary results so then we can return those summary results to SPRE and potentially analyze or go into more detail reporting or creating dashboards with those results. We also potentially want to use options message level equals I in order to better understand whether processing is occurring on the CAS server or if we're getting our data kicked back over to SPRE. I think of this as sort of a learning option, or really an option that we want to use for learning and better understanding. And whenever we use SQL queries, we want to use fed SQL instead of proc SQL in order to execute in memory on CAS tables. In this demonstration, we'll be exploring where our processing is being executed, whether it's in the SPRE environment or in the CAS environment. And we'll check out a few different procedures, data step 2, and SQL. We've just opened our demo2.sas program, which is in Lynn's home folder. And we'll go ahead and just execute these first few lines. What we're doing here is just loading some data into memory. We use procasutil to load the sales.xlsx file into memory in the CASUser Caslib. Then we use procmdSummary to create some summary statistics from the sales data table, so in-memory table. And we output that as casuser.salary summaries. So I'll go ahead and run this. We see the Cloud Analytics Services process the request. We've loaded the data up into memory in CAS. And now we'll execute a few different data steps. So first, we'll start with a data step that starts with a CAS table, but outputs a table to work.new. So we're loading data from a CAS library, but we're writing data using this data step to a SPRE library. So I'll execute this. We notice on the log, it doesn't say that it was executed on the Cloud Analytics Services, so this table was actually output in the SPRE environment. And if we go over to our libraries, we can open up the work library and see this table new is really a SPRE table on the SPRE environment. We'll now do the same thing, but instead of outputting our table in the work library, we'll output it in the CASUser Caslib. Now we can see we're running the data step in Cloud Analytics Services. It's this note we get in the log, and now we've output our data. And of course, it's in the CASUser Caslib. We have this data table new in the CASUser Caslib. We're going to change the options for the message levels just so we can see a little bit more results. We'll try and run this first data step 2 code. We're outputting data in CASUser, and we're reading data from CASUser. So it feels like it should work, but we're going to end up getting an error. The procds2 expects a seshref equals option to specify the CAS session. So we automatically started a CAS session at the very beginning of this code named my session. And we need to feed this session. Well, actually, submitted in the other code file that we ran earlier when we started our CAS session. And we need to feed this session to procds2 so that it knows which CAS session it's trying to execute in. So when we add the seshref equals option, we have all the other same code. Everything's the same. So our data is being loaded from a CAS library into a CAS library. So go ahead and execute this new DS2 code. And when we've used the seshref equals option, we no longer get an error. So it executed successfully, and we used procds2. It doesn't give us any information about the cat being executed on the CAS server, partially because it's multi-threaded. We'll now try this next statement, procds2 with a seshref equals option, but we're trying to write our data to a SPRE library. So we're reading from a CAS library, but we're writing to a SPRE library. We'll try and run this. We'll see that it does not work. So in this case, the problem is that we're trying to write our data all in one thread from a CAS library into a SPRE library. But these threads are really on different machines. The CAS machine and the SPRE machine are potentially going to be actually different computers. And even if it's all sort of folded into the same environment, they're going to be separate virtual machines from the point of view of the software. So in order to get this to work, in order to get procds2 to work successfully, writing data tables to SPRE, we have to use 2 different threads. So we basically create a procds2 program where we read in the data into one thread, and then we use a different thread to write the data in the SPRE environment. And of course, these 2 threads are going to be different because they correspond to different machines in the server environment. And I'll go ahead and make sure I turn on the message level options a little bit so that I can see that it's actually being executed in CAS. Note, DS2 running on CAS due to seshref. So this was the option that we were missing earlier since we didn't have this message level set to equal I. So if you want to see these messages about where processing is occurring, I'll encourage this options message level equals I. This CAS action completed successfully. It executed DS2, but it did output the data into the work library at the end of the day, rather than into the CAS library. We'll now explore some SQL code. So we'll just run proc SQL. we're using PROCSQL from a CAS table, but by default, it's going to execute in the SPRE environment with one exception. So here we get these results back and they're printed here, which sort of clearly tells us that they're printed at least in the SPRE environment. But we know PROCSQL is going to execute in the SPRE environment because it's not a CAS-enabled procedure. But let's look at the log. We turn this message level on so we could see this message. Note, the where clause is being processed by Cloud Analytics Services. So even though PROCSQL is executing in the SPRE environment, this subsetting where that we're selecting is actually executing in CAS. So the only data we're passing back to the SPRE environment is the subset data collected by the where clause. We'll now look at some proc fed SQL code. In this case, we are reading from a CAS library, so we feel like it should work, but we'll double check. And we're going to turn the message level down just a little bit here. Message level equals n. We get an error here because proc fed SQL expects a seshref equals option. So even though we're using a CAS table, fed SQL doesn't really know, the procedure doesn't really know where to find that CAS table because it doesn't have a CAS session specified. Notice, I like to point this out, and this is one of the reasons we're going through this demonstration, it doesn't tell us the exact error, which is you need to state a session ref. It tells us it can't find table CASUser.sales because this fed SQL procedure doesn't know about our CAS session. So we'll now give it information about our CAS session by specifying a session ref equals my session. That's the CAS session we started earlier. When I run this code, I get note fed SQL running on the CAS server. So we get these slight summary results passed back to basically the local SPRE environment just to sort of print them out in SAS Studio. But the CAS environment does all the processing to create this table. And if we go to the log, we do see that fed SQL is running on the CAS server. And we get 4 rows returned to SPRE, which are basically these summary results that we're analyzing, that we're looking at graphically in the local environment. Now we'll look at some CAS-enabled procedures, or we'll look at the difference between CAS-enabled procedures and the non-CAS-enabled procedures. Proc means is a CAS-enabled procedure, so our output is a CAS table, and our input is a CAS table, and we'll run this. We've got this message level equals I still, so we're going to see some messages. We see it, so we get our results for proc means, but if we look at the log, we see this note, the CAS aggregation.aggregate action will be used to perform the initial summarization. So in fact, it is executing this procedure on the CAS server, but the CAS server seems to have a different name for generating means. It's this aggregation.aggregate action. For more information on CAS actions, I'll refer you to my coworker Aurora's course on the CASL programming language. It's another one of these education tutorials associated with SAS Global Forum 2020. And we can see this data set, CASUser.salary summary, has been written out into our CAS library still. Next, we'll run proc sgplot. We'll execute this on a CAS table, but it's not a CAS-enabled procedure. It just does local plotting. So we'll run this code. We see the where clause is being processed by Cloud Analytics Services, but nothing else happens in CAS. So it basically just pulls the data from CAS based on the where subset and then plots these results locally. So we see here's our local plot. And the only thing that executes in CAS is just this where subset. Before we finish this chapter, I just want to point out a few more resources for documentation on programming in CAS and using DataStep in CAS. We'll go to support.sas.com/documentation. So sort of our home doc page. We'll navigate to Programming, SAS Viya, and SAS 9.4 and Viya. We'll be focusing on SAS Viya, of course. On this bar on the left, we'll open up Data Step Programming, and we'll go to Data Step Programming for CAS, which has some specific information that is useful for executing the data step in CAS. We'll open up Data Step Basics. It gives you some tips and tricks for running data step in CAS, some of the information that we've presented in this course, but it goes into some more detail about what is supported in the data step in the CAS environment. So if you're a data step programmer, if you use SAS 9 a lot and you've programmed a lot in data step and you're transitioning to CAS, I would think this documentation page will be very useful at learning what can transition over into CAS and what you're going to need to change to make sure that your data step executes, essentially more efficiently, that it takes advantage of the distributed computing processes we have. I'll also scroll up under SAS Viya Programming and look at Introduction to SAS Viya Programming. This just includes a bunch of different information about procedures and SAS programming that will execute in SAS Viya, execute on CAS. In the next demonstration, in the next sequence of demonstrations in Chapter 2, we'll be looking at some SAS visual data mining and machine learning procedures. But whatever you need to do in SAS Viya, whatever sort of programming task you need to accomplish, you can check out the documentation for it here on this page. And this focuses on what's happening in the CAS server and how to program for CAS. In this lesson, we'll explore some of the interfaces you can use to control SAS Viya and the CAS server, Cloud Analytics Services. In this case, we'll be doing a bunch of different examples building decision trees, well, really collections of decision trees, random forest models, using a bunch of different interfaces. We'll start by briefly overviewing a variety of SAS Viya application interfaces that you can use. Then I'll demonstrate how to accomplish decision tree modeling, while build random forests, using a number of these interfaces. SAS Viya contains a server process called CAS, or Cloud Analytics Services. CAS is a distributed multi-machine system for parallel processing of distributed data. This architecture allows you to perform complex computations on large volumes of data quickly. But to access and direct processing on the CAS server, you need to use some kind of client application interface. Both programming and point-and-click application interfaces are available. One of the point-and-click applications I'll demonstrate is the web application interface of Model Studio. This will allow you to build predictive modeling pipelines quickly and easily. I'll be showing you two other point-and-click interfaces as well. Here's a snippet of code from a Python program I'll demonstrate. SAS provides a downloadable set of Python methods for CAS that you can use as part of your Python code to connect to SAS Viya, submit processes that execute in Viya, and view and download results for further processing within your Python client application. This uses this Python package called SAS SWAT, the SAS scripting wrapper for analytics transfer. We'll talk about that in more detail in the demonstration. Programming interfaces for SAS Viya include SAS procedures and the data step code, Python, R, Lua, Java, and a REST interface that uses an HTTP protocol. No matter which client interface you use, including the point-and-click ones, the requests you specify are converted into a new SAS language called the CASL language, which includes CAS actions. You can also use CASL directly, and that's the syntax shown in the bottom right on this slide. CASL has an object-oriented syntax similar to Python, R, and other such languages. What I like to emphasize here is that regardless of how you submit your programming, whether you use Python, R, SAS procedures, or directly use the CASL language, it all gets translated into the same CAS actions. So the functionality you get in Python and the functionality you get in the CASL language are basically identical. Now I want to describe decision trees for a couple of minutes and then demonstrate building some decision tree models using a number of different SAS Viya interfaces. Since I'm using it as my example, I'll first give you a whirlwind overview of what decision tree modeling is. If you're new to decision trees, you're likely not to be able to take in all of the details here, but please don't concern yourself with that. Just keep in mind that the main objective is to give you a chance to see the wide choice of application interfaces in SAS Viya, and this is simply one objective. SAS Viya has broad capabilities. With statistical modeling in general, the objective is to predict new cases or outcomes based on measurable inputs. Statistical models are created using past data with known outcomes. But if you create a complex model to maximally fit the past data, it usually does not predict new cases as well as a simpler model, because the extra complexity is explaining random effects in the original data. So the model creation process usually includes techniques to remove some of the complexity so that the model generalizes better to new data. First, let's look at how decision tree models, once they've been created, are used to predict cases. Consider a dataset with two input variables and a binary outcome that we wish to predict based on the values of those input variables, x1 and x2. The binary target outcome is represented by two colors, yellow and blue. For a more concrete example, consider each dot is a bank loan to a customer, and yellow indicates that they defaulted on the loan, and blue indicates that they didn't default on the loan. X1 might be the debt to income ratio of the person who took the loan, and X2 might represent annual income. And we want to predict how debt to income ratio and annual income of a customer affect whether or not they default on a loan. In real-life decision tree models, you will typically have a large number of predictor variables. 2 is enough to illustrate how it works here and makes it so that we can plot it in 2 dimensions a little bit easier. To predict an outcome, decision tree models create rules that are applied in a stepwise order that can be represented like an upside-down tree, as shown here on the left. The rules create separate areas in the plot that maximally concentrate yellow outcomes in some areas and blue outcomes in other areas. Here, the first rule splits our plot into 2 areas along the x2 axis. One area above x2 equals 0.63, and one area below x2 equals 0.63. A second rule is then applied to each of those 2 areas that splits those areas further based on the values of the other input, x1. This leaves us with 4 different areas in the grid, each with a different proportion of each outcome. The proportions of each outcome in each area become our prediction of the likelihood of each outcome based on the values of x1 and x2. For example, for a new observation with values of x1 and x2 at the point indicated by the red circle in the plot, the decision tree model predicts that the color has a 70% chance of being yellow because 70% of the data falling into that box when we built the model were yellow, or people who defaulted on their loans. So how are these prediction rules created for decision tree models? To select useful inputs and to come up with the best hierarchical set of rules, trees use a split search algorithm. We'll now go into a little bit of detail on this split search algorithm. Here we assume a binary target, but the methods are available for other kinds of predictions, for example, a continuous target where we're just predicting some kind of number as well. The split search starts by selecting one of the input variables. So here we begin with x1. We look at the number of yellow and blue to the left and to the right of each possible split point for x1. We find the split point for x1 that maximally separates the 2 types of outcomes. Here, the value x1 equals 0.52 is the value that maximally separates the blue and the yellow outcomes. Then we repeat the process independently for x2 and all other inputs, finding for each input the best split point that maximally separates the blue and yellow outcomes. Here's the same white line that shows us the best split point for x2, and we see that it looks like the best split point is right around 0.63. So we have 0.63 is the best split point for x2, and we compare the best split point for x2 and the best split point for x1. After you determine the best split for every single input, the algorithm compares those best splits across all inputs to find the overall best split. Here we determine that the x2 splitter was better at separating the outcomes than was the x1 splitter. This creates our first decision rule. We split the points according to the rule x2 is greater than 0.63 or x2 is less than 0.63. So now we repeat the process for each subset on each side of the initial split. Determine the split point for x1 that maximally separates the 2 outcomes in this bottom subset, so values of x2 less than 0.63. Repeat the process for the x2 input in the subset. And for the subset, compare the best x1 and the best x2 splits to determine which of the 2 achieves the maximal separation. In this case, it was the split on x1. The data in the subset area is then split again based on the second rule. The process repeats in each leaf until there are no more splits that meet a minimal measure of effective separation. The resulting set of rules is known as the maximal tree. However, it's likely that the maximal tree fails to generalize well on an independent set of validation data. Basically, the maximal tree does really well at fitting data that it already knows the answer to, so these yellow and blue points that we're trying to build a model on. But when we go and try and score data that this model has never seen and that it doesn't know the answer to, it doesn't generate very good results. So we've selected useful inputs and split rules, But now we need to do some optimizing complexity to ensure we build a model that works well on new data. When the split search algorithm produces a model based on the training data, the result may have many branches that represent the most complicated model possible based on the chosen algorithm parameters. Usually, this model is too specific due to random effects of the training data and does not generalize well on new observations. To avoid potential overfitting, many predictive modeling procedures offer some mechanism for adjusting model complexity to remove random effects of the training data. For decision trees, this process is known as pruning. So the decision tree is created by applying the split search algorithm to the training data. But we hold back a separate data set, a separate subset of data with known outcomes, so we know the values of the target, to test the performance of the decision tree model on an independent set of data. We call this the validation data because we use it to validate our model to make sure that it works well. We create the most complex model on the training data, but then we prune it back in several stages to create simpler models with fewer splits. Then we compare how well each level of model complexity fits the validation data that we held back. So these stars indicate performance on the validation data. The simplest model with the best fit to validation data is selected. So we choose this model here with 3 stars because it gives the best performance on validation data. We choose it over the more complex model because we have a preference for simple models. Basically Occam's razor, where we want to make the fewest assumptions possible. For training data, the model improves with increasing complexity. However, it's typical that for validation data, the model fit is better initially as complexity increases, but at some point starts to level off and decrease. This is because the more complex models begin to explain patterns that are unique to the training data subset and do not generalize to the population of the sample that they're meant to represent. This is an example of overfitting in the machine learning terminology. An alternative approach to creating a single tree and then pruning it is to use ensemble methods. Ensemble methods create a new model by combining the predictions from multiple models. The commonly observed advantage of ensemble models is that the combined model is better than the individual models that compose it. Ensemble models for decision trees are referred to as random forests, or one example of ensemble models, sort of the naive example of ensemble models for decision trees are random forests. A random forest model is a collection of individual trees. Each tree in the collection is created at the training stage from an independent random sample of a subset of observations and variables from the training data. To validate the forest model, each tree is then applied to predict outcomes for each observation in the validation data. The final predicted outcome is based on the average prediction across all trees. This is also how the forest model is used when it's deployed. Individual decision trees in the ensemble do not need to be pruned because the ensemble model tends to be more generalizable because it aggregates information from a diverse set of trees and therefore gives better predictions than any specific tree. So now we'll do some demonstrations on how to build ensemble forest models using each of these application interfaces listed here. These are basically the different tools that we'll be using to build our predictive models. We can use point-and-click tasks in SAS Studio, that's a graphical interface. We could use CASL programming language, that's of course a programming language. Python and SAS SWAT, another programming language. We could use SAS procedures, which is sort of the old school SAS programming language. We could use SAS Visual Statistics, a graphical interface, or Model Studio, another graphical interface. Here's a description of the variables in the dataset that we'll be using to build the forest model. It's a home equity line of credit dataset named HMEQ, for home equity for short. The table contains one row per loan for each customer. For each loan or customer, bad equals 1 for loans that are in default or delinquent, and bad equals 0 if the loan is in good status. The target is bad because it's bad to default on a loan, but it's also bad for binary applicant default. The value of bad will be the binary target variable we will model with the forest models, using the rest of the variables as input. So things like the debt to income ratio, or their home value, or their years on the job. We'll get started with the demos. So we'll have 6 different demos demonstrating 6 different graphical interfaces for building random forest models. Our first demo is building a decision tree model, or really a random forest model, using SAS Studio tasks. We'll go to SAS Viya, SAS Studio. We'll sign in as student, and we won't sign in as administrator. Before we look at any tasks and build our models, we have to load up the data. Here in our home folder, under SGF20 VIY, the course code for this workshop, we'll open up the load HMEQ data.sas. This is just some code to create a connection. It basically creates a CAS session for us and loads up some data into our CAS user Caslib. So if I run this code, the output just tells me that I've loaded up some data, and we can see if I go over to libraries, here we have the CAS user Caslib, and there's this HMEQ data table with all of the inputs we were expecting. We're now going to look at some tasks. So we'll click this tasks icon. We see a number of tasks available. Things like connecting to CAS. We'll be doing SAS Viya machine learning. So I'll open this up. I'll open up supervised learning. Oh, I was actually under SAS Viya statistics. I wanted to show a decision tree. So I'll open up this decision tree task real quick. When I double click this decision tree task, it opens up this new object, decisiontree.ctk. It allows me to specify the data set that I want to use. I'll use CAS user HMEQ, and I can specify whether I want to include validation data, what sort of targets that I want to include, and then I can go over to options and specify options associated with the decision tree. We'll go ahead and close this and load a forest task that we've already created, so we don't have to spend a lot of time clicking options. But I wanted to highlight this graphical interface that allows us to select options for our predictive models. I'll go back to this Explorer, and notice we have this forest task.ctk file in the SGF20 VIY folder. So I'll double click this forest task. This will open up a task where I've already saved it. So these options were options that I'd already saved on it. We're using the CAS user dataset. We'll be including validation data, 70% training, 30% validation. Our target is binary applicant default. We'll use the rest of our things as all of our continuous inputs as inputs, all of our continuous variables as inputs, our two nominal variables as nominal inputs. Under options, we'll be building 1,000 trees, a couple of different forest options. We'll leave these options as the default. We'll go into output. We'll save the scored data as a CAS table named scored data, and we'll actually call it CASUser.scored data. We'll go ahead and click overwrite just in case there's already a table. We'll only include variables used in the analysis. And we won't save the model or the scoring model. Well, we'll go ahead and save the model. I'll name it casuser.rf for random forest underscore model. I'll include this overwrite data. The thing I wanted to highlight before I run this is that this generates code on the back end. So even though we've filled out our options in a graphical interface, we specify various options we want associated with the random forest. In fact, what we're doing is we're using a graphical interface that renders code. So it runs this proc forest code, partitions the data into training and validation. Our targets, our inputs, a couple of different options that we have, how we want our scored output data to look. In addition, it'll plot some fit statistics, as well as variable importance using sgplot. So we'll run this, and it'll run all this code. This is a nice way to learn the code too. You can use the graphical interface to select the options that you want, but then you can see what sort of code actions that it'll create, what sort of SAS code that it'll generate. Now that it's finished, we can look at the results, and I usually like to adjust the way the pane looks. Oh, here we are. Oh, this is it. And under results, we'll see some model information, 1,000 trees, 4 variables per split for each tree. This is information about the trees in the forest. We had about 4,000 training data cases and about 1,800 validation data cases. We see variable importance. Evidently, the most important variable for predicting whether or not people will default on their loans is the debt to income ratio. The least important is the reason that they want the loan. We see fit statistics as a function of the number of trees, but instead of reading this table, I'll scroll all the way down, we can look at this same information in a plot. I'll actually rebalance the size of my objects a little bit so the plot's more visible. Sorry, I'm just reorganizing my SAS Studio layout just a little bit. We can see the average squared error as a function of the number of trees. It's much lower on the training data. The one that we're interested in is the validation data. And we have this extra sample called the out-of-bag sample, which there's some details on this if you want to look this up about random forest. It's basically another version of data that the models haven't seen before. We also have a plot of that variable importance table that we looked at. These sgplot procedures that we ran were rendered automatically by this forest task. Now that we've built the model, we want to do some assessments of the model. So we'll go back to tasks. Real quick before we go back to tasks, the model that we specified, or really the scored data that we generated, was a data table casuser.scoredData. I'll be using that in a little bit. We'll go to the tasks. Under SAS Viya evaluate and implement models, we'll open up the assess task. This allows us to assess scored data. So our scored CAS table is no longer casuser.hmeq. It's going to be casuser.scoredData. You can see that RF model table we created in addition. For roles, we do have a nominal target, and our target is bad, binary applicant default. So I'll select bad for the target. The event level is going to be 1. We want to predict whether people are going to default. That's a 1. The posterior probability of the target event is the prediction generated by our model. We didn't exactly look at this, but I happen to know what it is. P bad, the probability of bad, classifying as binary applicant default. So we'll select this one. We'll look at some options. We don't need to specify any additional roles. I'll just unselect lift chart because we just want to look at ROC chart. We'll go ahead and leave the rest of these options as their default. I'm not really worried about saving the output information, although I can if I want. So I'll go ahead and run this. Real quick before I run it, it generates the assessment data using PROCs, and it plots the ROC curve using PROC-SGPlot. And then it makes sure to delete the temporary data tables afterwards. We'll run this. Again, let me just rebalance how much space I have here. We see these are the assessment tables, I guess, that are generated. We don't plot the lift table. So this is a table with information on depth and cumulative lift. So it's a way to judge how much better a model is than a random guessing model if you're only selecting a certain percentage of the observations. And we have ROC information. When you select different values for your probability cutoffs, what true positives, false negatives, and true negatives do you get? Essentially, how does your model perform at different cutoff values? And as well as that, we can plot the ROC curve. This is the ROC curve on the entire data set. So we've looked at all of the scored data. When we built the model, we split it into training and validation data. But this ROC data is actually the full data set. So we might want to just restrict this to the validation data in order to get an unbiased assessment. This is going to be a little bit of an optimistic assessment for the ROC curve. That's pretty much all we're interested in here. Some assessment statistics for our model. We could pull out all sorts of different assessment statistics from these tables here. In particular, we can look at the cutoff, and we can look at different misclassification values for different cutoff values. Evidently, just looking at this data set, we have the lowest misclassification right around here, which is about the 0.5 cutoff. So if we say everyone whose probability is above 0.5 will default on their loan, and everyone whose probability is below 0.5 will not default on their loan, that'll give us the best classifications with about a 7% misclassification rate. In our next demo, we'll explore building this same random forest model using SAS Visual Statistics. In this next demonstration, we'll build a random forest model using SAS Visual Statistics. We'll go up to this top left Show Applications menu in SAS Studio and go to Explore and Visualize. When I click it, you can see it takes me to SAS Visual Analytics. Visual Statistics is just a subcomponent of SAS Visual Analytics. There was some unsaved report. We'll just click No. We don't want to load someone else's work. We'll hope that they saved their work if they cared. So we'll start by creating a new report, and we'll start by adding some data. So I'll click Data here. This opens this Browse Data menu. I could load up the HMEQ data table, but it's already here in memory because we've been using it throughout this course. So I'll click it, and I'll select OK. In fact, we loaded it into CAS user Caslib with that SAS Studio code that we submitted a little bit earlier in the previous demonstration. We start out, we can go to Objects here. If we scroll all the way to the bottom in Objects, here under SAS Visual Statistics and SAS Visual Data Mining and Machine Learning, here's our machine learning algorithms. We'll use the random forest algorithm, so we'll grab this forest object, drag and drop it into the middle. It wants us to assign some data and roles. So here on the roles option, we'll want to specify a target and some input variables. Before we do that, let's just do a little bit of data preparation. So I'll go over here to data. Notice that binary applicant default is a binary variable. It has zeros and ones. Visual statistics or visual analytics automatically identifies this as numeric. We want this to be treated as a category. So I'll open up the properties here, and I'll change this from measure to category. And you can see now bad appears up here as a categorical variable. In addition to doing this, we want to add a partition variable. So I'll click New Data Item, Partition. I want to generate a partition based on sampling, but I don't want to do a simple random sample. I want to do a stratified sample. I want to stratify based on the target, binary applicant default. I want to have equal proportion of the target in the training data as in the validation data. For our training data, we'll use 70%, and I may as well include a random number seed. Well, I'll let the software choose its own random number seed, actually. I'll go ahead and click OK. Notice I now have a new variable named partition, and I can now specify roles for my random forest. Our target is binary applicant default. Our predictor variables are all of our inputs, so I just click the first one, hold Shift, click the last one, select OK. And for partition, well, there's only one option. I created the partition variable, so it knows that this is our partition. Notice when I add the partition, we now get training and validation data instead of just training an out-of-bag sample. I'm going to do a few changes to some options on the forest, just so we can make sure it matches the forest we built in SAS Studio. I'll specify 1,000 trees. It's retraining the model now. But while it's doing that, I'll also change the maximum levels. This is how deep the decision tree is allowed to be, so I can hover over here. Specifies the maximum depth of the tree. So we want a decision tree. This is saying our decision tree can't have more than 6 different splits in it. Let's allow for slightly more complex trees. So we'll specify this as 20. So each of our trees in our random forest model can be up to 20 levels deep with 20 different splits. And we'll leave the rest of these settings at their default. Takes a sec to train these 1,000 trees. And we can see here we really are training 1,000 trees, because here on our error plot it goes out to 1,000. But we probably could have only trained a couple hundred and we would have gotten similar performance. Once again, we identify that debt to income ratio has the most importance. It's the variable that's most important at predicting the target. And here it's defaulting to show us the KS statistic, which is sort of a separation on the ROC curve from a random guessing model to the model that we built. We could change this to validation data misclassification rate. So our model has about a 9.5% misclassification rate on the validation data. We can also change this confusion matrix to show us ROC information. So we see here's the ROC curve on the training data, and here's the ROC curve on the validation data. It's really good to separate these curves, which is of course why our software does it automatically for you, because you really care more about performance on the validation data than you do on the training data. It's good to make sure you build a good model, but ultimately the validation data tells how well your model is going to work on data it's never seen before. Once we've built this model, we can do a couple of neat things. One that I really like is if we open this More option, we can duplicate as another model. And if I hit Alt, it allows me to duplicate on a new page. So if I click Duplicate as a new page on Decision Tree, it's going to build me on a second page a decision tree model using all of the same roles and settings as the random forest model. So now, and of course I could right click on this to switch it to ROC. We see the decision tree model looks a little bit weaker than the random forest model, but one advantage is that we have this interactive decision tree to explore and even modify. So I could right click. Oh, it won't let me enter the interactive mode with validation data, so I'd have to change this a little bit. But I have some options to explore this decision tree. We see most of our customers are flowing over here because most of our customers don't default on the loan. So most of them we're classifying as blue, which means they're not defaulting on the loan, which is good because as a bank, we don't want to be giving out primarily loans to people who are going to default on them. We can save this report using the Save button. So I'll just save this as Forest Decision Tree, since that's a forest model and a decision tree model. I think of visual statistics as really designed for building things to show to people. So even though we built these models here, I would generally use these models to sort of show to executive leadership or a manager what work I've done, or to convince someone to make some sort of business change. If I wanted to actually build models that I'm going to deploy on some large new data set, I'll end up using Model Studio, which is the next graphical interface that we'll be talking about. In this next demo, we'll build a random forest model using SAS Model Studio, a graphical pipeline tool for building and deploying predictive modeling algorithms. We'll go to this Show Applications menu in the top left. Instead of explore and visualize data like we did last time, we'll do Build Models. This takes us to Model Studio. And we'll go ahead and open up our HMEQ Forest project. We could create a new project from scratch, but it'll be a little easier to start with some work we've already done. And I'll explore these results and show you what we've done. When I first open the project, I see what I like to call the Data tab, which is basically just a bunch of metadata that Model Studio knows about the variables in the original data set. So here's the variable bad, binary applicant default. I've actually already specified that it's a target, but it's now locked for me because I've run this project before. It also identifies that it's a binary variable. Notice it identifies some interval variables as well as some nominal variables. Some of these are numeric, but they only have 11 levels, for example. So the software has decided that it's really better to treat this numeric variable with only 11 different numbers as a categorical variable. And thus the metadata is set to have it specified as a nominal variable. We'll go over to the Pipelines tab. We have the option to create multiple different pipelines. For now, we'll have a very simple pipeline. We have data feeding into a random forest model, which goes into model comparison. If I click on the left, we see all kinds of nodes. We have data mining pre-processing nodes. We can do things like feature extraction, principal components analysis. We can do things like text mining, generating singular value dimensions from text columns for predictive modeling. And things like variable selection and imputation, which are what I kind of think of as core predictive modeling tasks. I always like to highlight there's this new node, feature machine, it's sort of new in this software version, that's very exciting because what it basically does is tries to figure out the best features to extract for your predictive modeling algorithm and then generates those features. So it goes through a bunch of different types of features and generates the ones that end up creating the best predictive model. We also have a bunch of supervised learning algorithms. Here's decision tree. Here's the random forest node that we're using. We also have gradient boosting models, which are another ensemble of decision trees, simple linear and logistic regression models, neural network models, this very exciting node, model composer, which basically builds a bunch of different models and compares them and selects the best one. So I always think the most naive modeling algorithm would be feature machine to let the software figure out the best features, followed by model composer to let the software figure out the best models. That'll essentially let the software do its own experimentation to figure out the best models. We have some post-processing nodes to ensemble, so we can ensemble models together, as well as some utility nodes, miscellaneous, exploring data, integrating open source code, integrating SAS code, saving and scoring data off. When we click the forest node, I'll go ahead and close this nodes here on the left. When we click the forest node, we see some options. We see we have some tree splitting options. So things like maximum depth equals 20. We're going to build 1,000 trees. I've set these to make sure we're using the same settings as we did when we built our other forest models. We have a bunch of different options that we can specify, just like we did in the other graphical interface when we used the SAS Studio task, or when we used visual statistics. Often I find we have more options here in Model Studio than we do anywhere else. simply because it, well, except for in code, simply because it surfaces as many options as possible. This is sort of the premier modeling tool for building complex predictive models here in SAS. We also have the option to perform auto-tuning, where it figures out the best settings for the models automatically. And I'm just going to turn on some model interpretability options. I'll just turn on global interpretability. PD plots has already been turned on. I'll just look at some model interpretability results. I'll right click on the forest, select results. Oh, and I would have to run this to rerun it, but I've already run it, so I won't wait while it's running. This green check mark indicates that it's successfully been run. And if it hasn't been run, you can't check the results anyways. So I'll check the results here. We see the error as a function of the number of trees in the model. We can make it full screen to see the legend. Training data, validation data, out of bag sample. This is the same plot that we saw in Visual Statistics and using the SAS Studio task. We also have the same variable importance table. It tells us the debt to income ratio is the most important variable. We also get score code, so we get data step score code as well as DS2 score code from the random forest model. These are useful. We can copy these out for deployment. Tells us the required inputs for scoring and the outputs generated by the model. Here's a list of all the properties. We could have checked that on the previous page. These are what we specified. Here's the SAS Studio code that would be used to train the model. I mentioned the SAS Studio tasks is a good way to learn the code. This isn't really as good of a way to learn the code because you can tell that it's clearly computer-generated code, but it does use the SAS procedure, proc forest. We can go to the assessment output to look at lift plots and ROC plots. This is the plot we're primarily interested in, ROC and training data, ROC for validation data. Evidently, we're building a pretty good model here. This is basically the same plot we saw in Visual Statistics. We also get fit statistics, and the most interesting one to me is always the misclassification rate. About 9% misclassification rate on the validation data, which is exactly what we saw in Visual Statistics, because we really are building the same model. We've got some more options here in Model Studio than we did in Visual Statistics, though. We can go to this model interpretability report and see these partial dependence plots. What this is showing is basically the average target prediction for different values of this input. So we see as debt to income ratio gets above 40, our probability of churning is increasing. If we look at credit line age, as our age of our credit lines increases, our probability of churn, and this is age in days, is decreasing. So people who've had credit for, excuse me, I said probability of churn, this is probability of default. I was thinking of a different data set. So as our debt to income ratio goes up, our probability of defaulting on the loan goes up. As the age of our credit line goes up, our probability of defaulting goes down. So people who've had credit lines for a longer period of time are less likely to default. Our new customers are more likely to default. These partial dependence plots are a really nice way to get sort of a broad perspective of what your model is thinking about different data sets. We have some references and some papers, as well as a YouTube video that goes into more detail on model interpretability tools. Those are included as a link in the course notes. We can close the results to go back to the pipeline. The model comparison node allows us to compare multiple different models. Here we're just sort of trying to show the same forest model in a bunch of different interfaces, so we won't build a complex comparison pipeline to compare a bunch of different predictive models, but that is the goal of the Model Studio interface. In our next demonstration, we'll show using Python to call SAS Viya models on the back end and build the same random forest model, of course. We'll open up the Start menu, open up Anaconda, and open up Jupyter Notebook. This opens up the Jupyter Notebook browser, and we'll go ahead and from the home page open up the Python Forest notebook. I'll go through this Python Forest notebook and explain what's happening here. We start by importing necessary Python packages, so popular Python packages like pandas and matplotlib, as well as this SWAT package, which is how SAS is going to be connecting from the Python interpreter to the SAS Viya CAS server. So we have this SWAT method here called CAS to make a connection, this connection object, to the CAS server. So we're connecting to our server with alias server on this port using username and password. We're not using any security settings, but we could absolutely use certificates and token authentication. Once we've made our connection to the CAS server, we'll load up some data. We'll use this read CSV method through this connection to essentially read this CSV file into a pandas data frame and then load up that pandas data frame as a in-memory table on the CAS server. By default, it's going to load it into Caslib CAS user. Since I specified replace equals true, it gives me this warning that I'm actually replacing this table because I'd already loaded it. I already had the HMEQ data table in the CAS user Caslib. We'll load the sampling action set. I think of this as sort of like loading Python modules, but it's for CAS actions on the CAS server. And we'll see some examples of using CAS actions in CASL code in the next example, but here we'll be using these CAS actions from Python. So we've loaded up our data as an in-memory table, and now the first thing we're going to do is submit the sampling action or the stratified action in the sampling action set to do a training and validation sample. So we have 70% of our data as training data, and we want to group by the target, so we have stratified random sample. And we want to output the data table as the existing data table, just overwriting it and appending the new partition variable. So this basically goes to the HMEQ data table on the server. So even though this is Python code, all of the processing is happening on the CAS server, and it adds a partition variable. We can see that here's basically the partition. Here's our validation partition. Here's our training partition. We're now going to use the cardinality action set to find our class and interval variables. Basically, we're preparing our data for predictive modeling. So we're going to use this cardinality action set to get basically a little summary table. And here's our summary table that we're going to get. We're going to bring that summary table locally to Python so we can extract which variables we want to use as our target and which variables we want to use as our inputs, and then, of course, what our partition is. Basically, this is setting metadata like we did in Model Studio on the Data tab, but we're just writing all these Python variables. So we have this variable named target that contains just the string bad. We have a variable inputs that contains all the inputs. Here they are. And a variable nominals that contain all the nominals, inputs and targets. Basically, most of this is just Python code to extract information from this data card data frame that we brought back from the server. So we created our data on the server, and then we're bringing it locally as a Python data frame. We're only doing this to this summary data set, not to the original data set, because we want to take advantage of the distributed computing on the CAS server. I'll load the decision tree action set so I can build a random forest model. And here I'll use the forest train action in the decision tree action set to build a model on the training data. So part int equals 1 is on the training data, so we have this where clause. Our target is bad, our target. Our inputs are all of our inputs. We specify the nominals. We'll build 1,000 trees. Each tree will use about 60% of the training data to build each tree in the random forest model. We'll split based on variance for predicting our target, and our maximum number of levels will be 20. So these are all basically the same settings that we specified for all of our other forest models, the one we built in Model Studio, the one we built in Visual Analytics or Visual Statistics, and the one we built using the SAS Studio task. We'll output our model table as this rf_model. And of course, we'll replace it because I may have named a table like that earlier when I used the SAS Studio task. When we build this forest model, it passes some results in this forest object, and we can extract some of these results. One of them is decision tree variable importance info. So here is our variable importance table that we looked at earlier, and we'll bring this table locally to Python for plotting. So here's just a bunch of Python code to plot the forest. To plot the variable importance for the forest model, And here we see our variable importance table plotted in matplotlib. In addition to building our model, we want to score it on the validation data. So that's what we're doing here. We're using the forest score action to score our random forest model, specifying that our model is stored in this table, rf_model, which was just the output of the forest model that we built earlier. In addition to that, we want the error from the tree, so we want to output some information about the error from the tree, as well as copy our target variable over to compare our predictions to the true value of the target on the validation data. We'll just look at some of these results. In particular, we'll bring back the error as a function of the number of the trees locally to Python to generate this same plot, average squared error by number of trees. This is only the error on the validation data. We would have had to do a little bit of extra programming to gather the error on the training data, as well as the error on the out-of-bag sample. But we're most interested in error on the validation data, so we'll just go ahead and look at this plot. We also want to generate assessments like lift and ROC, So we'll load the percentile action set and use the assess action, similar to the assess task in the SAS Studio graphical interface we used. We'll use the scored data table. So if we go up to scored model, we'll output the scored data as RF underscore scored, which of course is just the predicted variable, the predicted value for each observation versus the target value, the true value of the target. And we'll apply the assess action to it on it, specifying that our inputs, which is the predictions, are P bad 1, P underscore binary applicant default 1. And then the true value is the target variable, binary applicant default. And our event level is 1. And we'll output these RF assess tables. We create RF underscore assess, which is lift information, like we saw in the SAS Studio task, and RF underscore assess ROC, which is ROC information. We'll bring the ROC information and the lift information locally just to look at these tables. So this is the exact same table we saw in the SAS Studio task. We have depth, and we can look at cumulative lift to see how much better our model is doing than a random guessing model if we select 5 or 10 or 15% of the data according to the predicted probabilities. Or we have this ROC information for different values of the cutoff. So if our probability cutoff is 0.01, how many true positives do we get? How many false positives? How many false negatives? How many true negatives? We'll bring this ROC data locally to plot it, and we'll plot the ROC curve. Note that this is the ROC curve on the validation data because we only did the assessments on the validation data. This is all just local Python code to plot this ROC curve. So we created this ROC assessment statistic, essentially assessment statistic table on the server using the assess action, but then we brought it locally as a data frame to analyze locally in Python, and then we're plotting that data here locally in Python. We can do the same thing for the lift curve, although we didn't do it for any of our other models. And that's basically the same information that we generated from Model Studio or from Visual Statistics or from the SAS Studio task, but now we've done this using Python code. Even though we're using Python code to submit all of these actions, we did not build this model in Python. This model was still built on the SAS server, the CAS server, and it was built distributed. If we have a distributed CAS server, we're going to build this model on distributed data. So we are still taking advantage of the fact that we have this distributed cluster for processing our data, but we're able to use Python code to make our submissions. In the next example, we'll see doing the exact same thing using CASL code. So we'll submit these same actions, things like percentile.assess or decision tree.forest score or decision tree.forest train, but we'll actually use SAS code, which is the CASL programming language. In this last demo, we'll go back to SAS Studio and build our same predictive models using these CAS actions from SAS Studio. So I'll go back to Model Studio tab. I'll go to the Show Applications menu, and I'll go back to Develop SAS Code. This takes me right back to SAS Studio. We're looking at the results from the forest task that we built a little bit earlier. In this case, we'll go back to the Explorer, and under SGF20 VIY, we'll open up forest with CASL.SAS. So even though this is a SAS program, it does not use SAS procedures. Instead, it's going to use the CASL programming language. I'm just going to change my tab layout here real quick. This is my preference to see all the code, and then we'll see the results separately. So we'll start by creating a CAS session. So we're going to end our previous CAS session and start a new CAS session by specifying our CAS user Caslib. We'll go ahead and run this. We create our new CAS session and we've connected. And now I'll talk through the code and then I'll just run it one by one. We're going to import our data. So our hmeq.csv file, we're going to import it into work.hmeq. This is basically taking a CSV file, loading it into a SAS library. This data step then loads the data from a SAS library into a CAS library, the CAS user Caslib. We in fact don't have to run any of this. We'll go ahead and do it for good measure, but I just wanted to point out we've already loaded the HMEQ data table into the CAS user Caslib. The rest of our code, rather than using various SAS procedures, we'll use one procedure, PROCs. We'll use a bunch of different action sets, just like we did in Python code. We'll use the table action set, the sampling action set for generating our sample, and the decision tree action set for building our forest model. We'll use the sampling action set to do a simple random sample. We probably should have done a stratified random sample, but we've chosen a simple random sample here. We could have chosen a stratified sample. just maybe forgot to do so when we were building our predictive model. Now we'll go ahead and build our predictive model in the next action, but before we do that, we just want to use ODS output. Oh, excuse me, not what I wanted to click. We want to use ODS output to select the dtree_var imp info, which is the variable importance information table that we were interested in. It comes with our model, but by default, that output is not captured. So we'll use this ODS statement to capture it. We'll now go ahead and actually build our model. So we'll use the forest train action in the decision tree action set, just like we saw in Python. We'll specify our table, HMEQ, where part int equals 1, so our training data. We specify all of our inputs. We specify our targets. We specify basically all the same options that we did in Python, and we specify run to build our forest model. We then want to change our ODS graphics so we can plot our variable importance information. So I'll go ahead and run everything up here so we can look at some results. We see we get the information about the forest model that we trained. We get our variable importance tables, and we get the SGPlot results for plotting our variable importance table. We'll now move on to score our model, and I'll just run the rest of the code all at once. So I'll just talk about the rest of the code and then run it together. So we started here. I'll just click enter so I can make sure to find this again. We use the decision tree action set, forest score action. We score our validation data and output it as scored data, as a CAS table named scored data. Oh, actually, we'll output it as a CAS table named validation score, and our table name will be scored data. So it's a little bit confusing. This table scored data is actually the model table. We'll go ahead and plot the average squared error by the number of trees, which is a result we get from the scored action. So when we scored the validation data, we did see average squared error by number of trees, but we have to use ODS output to capture that. Next, we'll use the percentile.assess action, so just like we did in Python, to compare on the scored data, so data that's scored on the validation data that's been scored, to compare our prediction for the target, for the true value of the target, and we'll plot ROC and lift information. So I'll go ahead and run all of this CASL code. And we call this CASL code because it's all using proc CAS. But you can see it's really submitting the same CAS actions, Cloud Analytics Services actions, as we did in Python. So I'll submit this while it's running. I'll just talk a little bit about really it's the same actions. Oh, we get an error on work.errorMetricInfo, but we're still able to build our model. And here's our prediction error for forest as a function of the number of trees. So rather than looking at this long table, we'll just look at the plot that we had. Oh, we missed the plot. I think we forgot to actually call SGPlot to plot it, so we'll skip that. We get our plot for the ROC curve, as well as our plot for the lift curve. The exact same plot, and I'm actually going to just go back to point out, the lift curve has a slightly unique shape. It's actually the exact same lift plot as we saw in Python. It's just plotted using a different interface. So if we go back to the CASL code, what I like to emphasize is that these actions, these CAS actions, they can be submitted using a variety of different interfaces. So we've showed that you can submit the exact same CAS actions using Python code or using the CASL code. As it turns out, when we built our model in Model Studio and in Visual Statistics, it submits the same CAS actions on the back end. So it's organizing these CAS actions in a graphical interface for us. But at the end of the day, these are what gets submitted to this CAS server for processing. In fact, even in this forest task, where we have this SAS Studio code, so if I look at this code is proc forest, so it's a SAS procedure. But in fact, when it executes on the CAS server ends up translating it into these CAS actions. So this SAS code ends up getting translated on the back end into something that the CAS server can understand, and we build the same models in all cases. That's the end of our demonstrations of using a bunch of different interfaces. I only had 5 demonstrations, even though I mentioned 6 interfaces, because the forest task, in addition to using the graphical task-based SAS Studio interface, we've also rendered SAS procedural code on the back end. So those are our 6 interfaces. Thanks so much. So in the previous demonstrations, we saw these 6 different ways to build the same random forest model on the CAS server. We used some graphical interfaces as well as some programming interfaces, but we ended up building the same random forest model in all cases. And in fact, we used the same in-memory CAS library, the CAS user CASLib, throughout all of them. And at the beginning of each of these methods that we used, we loaded up the data using essentially whatever local method there was to load the data. But in fact, the data stayed on the server the whole time. So when we loaded up the very first data table for SAS Studio, the HMEQ data table that we analyzed in SAS Studio, we could have just used that same table using all of the different interfaces. This concludes our What is SAS Viya course. Thanks so much for attending, and if you have any questions, feel free to reach out. Thanks.